Welcome to the 3x5x Mission Chronicles series. I'm Mark Raymond, Division 39 Chief Engineer for Operations and Science, and I'm one of the organizers of the series. Before we get to today's talk, I'll mention that our next Mission Chronicles presentation will be July 21st at 5 minutes after noon. Bruce Wagner will tell us about Voyager at 45, Engineering the Endgame. And in the August Mission Chronicles talk, Linda Spilker will explain the unique science Voyager is doing. If you have a topic that would work well for this monthly series, please let me know. As an inducement, you may be interested to know our speakers get many impressive perks. One benefit is that our Mission Chronicles team works with line management, and we can guarantee that the speaker's next raise will be greater than 12%. Now for today's talk, Susie Carrera is our skilled WebEx host. Among other things, she'll manage the questions at the end of the presentation. All you have to do is type in the Q&A area that you have a question. You don't even need to type out what it is because Susie will unmute you so you can pose it to Lukas yourself. Dr. Lukas Mandrake is the supervisor of the Machine Learning and Instrument Autonomy Group in Section 398, as well as the Machine Learning and Science Autonomy Strategic Lead for the Information and Data Science Program. He's also the data science co-lead of SUDS, the Science Understanding Through Data Science effort, along with Susan Owens. Lukas has been at JPL since 2002, and his research efforts include enabling new missions through onboard science autonomy, revealing subtle relationships through interpretable machine learning, and raising the standards of practice for all JPL data science. Finally, before Lukas begins, I need to correct a tiny error. I should have said earlier that we can guarantee the speaker's next raise will be less than 12%, not greater than 12%. Okay, now with that simple detail out of the way, I'll turn this over to Lukas to tell us about science instrument autonomy, an emerging technology ready to enable new mission science. Lukas?
Thanks very much for that, and hello everyone. Today we're going to talk about what's required to do science at extreme distances or in very remote locations. But rather than talk about rockets, sensors, or power, we're going to talk about bold new flight software smarts and the missions that it can enable. Science instrument autonomy. Let's set the stage. Imagine that you are going on a long trip of discovery into unknown territory. You've been equipped with the best in science gear and training possible, taught what to look for that might advance science understanding, and warned of potential dangers. But here's the first catch. You, your notes, and your observations aren't coming back. This is a one-way trip. And you only get 5 predefined one-hour chances to call home. How would you spend those precious communications opportunities? What would you choose to report back? How could you make sure your words were efficient, precise, and clear? And what advice would you hope for from home base in response? This is analogous to the bandwidth barrier challenge for space science, and what onboard systems we'll discuss today must solve. A brief summary of today's discussion. We'll define onboard science autonomy by its primary drivers and differences from conventional autonomy. We'll use some of our work from the Ocean Worlds Life Surveyor project to demonstrate our guiding principles of trustable science collaboration. We'll introduce a NASA framework we're building to help initiate and coordinate the growing community, and explore the evolution required in mission operations to control these advanced onboard systems. Finally, we'll leave you with a glimpse of a radical new mission concept enabled by these approaches. But before we do, here's a moment of inspiration from a project called the Ocean Worlds Life Surveyor, as a concrete example of onboard science autonomy need. Bear with me for this beautiful 3-minute video. For the kind of instruments that we'd like to send to gather smoking gun evidence of life, the raw data on board can be 10,000 times larger than we can transmit back to Earth. The barrier between us and those distant missions that's posed simply by the speed of light and by the dimness of those signals is the major barrier to scientific inquiry in deep space today. Fortunately, there's a solution. Onboard science analysis systems are designed hand in hand with the mission science team and can directly assist during instrument construction and final deployment onboard missions to distant worlds.
Each of these ocean world environments offers unique challenges that are going to require creative engineering solutions to solve. But this means that things like onboard data processing and prioritization are even more critical when it comes to missions that are exploring in orbit around Jupiter, Saturn, or beyond.
There's been so many advances in instrument development that we can take enormous amounts of data at very little expense. And so what this autonomy is all about is prioritizing the most interesting data so that you don't waste your data budget on a bunch of identical frames.
To use a musical metaphor for the general approach, we can extract and transmit the sheet music and lyrics. Then we can take a few representative samples of what each instrument sounds like from the raw data and reconstruct the whole song on the ground.
You don't even know what you're looking for because you don't know if there's life there or not. And you're looking for things that are probably microscopic life at best because we know that there's not macroscopic life walking around on the surface. But if we have multiple lines of evidence, then we have a strong argument for whether something is alive or not.
So the work that we're doing with OWLs, developing this instrument suite, combining it with microscope and all of these detection methods to look for evidence of life is of course extremely challenging, but I'm sure that we have the right team to do this work.
That kind of exchange, that dialogue between the science team and the spacecraft is really going to be enabled to be much more efficient because of these technology developments we're working on for OWLs.
So the spacecraft of the future should have the capability to process the raw data on board in order to identify those data sets that are most responsive to the scientist's interest and make sure that these are prioritized for them first.
And the autonomy capabilities that OWLs is developing is going to be what gets us there, to ask the civilization level science question: are we alone?
Thank you for coming on that brief journey with us. Let's get back to the talk. So let's define science instrument autonomy by discussing its definition, drivers, and what it offers us. Onboard science autonomy is concerned with the acquisition and contents of the science instrument data itself. It can recognize both known and unexpected targets of potential interest, efficiently summarize vast data records, and prioritize the most informative findings. By doing so, it allows a mission to react in real time to scientific events of interest, as well as use bandwidth efficiently. And this provides a new mission formulation trade, less required bandwidth for more onboard capability, all with the goal of maximizing a mission's scientific productivity, as well as enabling new classes of science capture and mission concepts. This is not the control loop autonomy you typically hear about, and it's separate from, but synergistic with automated planning and scheduling. Note the graphic at the bottom taken from a report on NASA autonomy. In this cartoon, humans are represented as a last-ditch safety net in case things go wrong. But when it comes to science, we can't take this approach because science isn't automatable. If we really want to use conventional autonomy language to describe science autonomy, the state we're estimating and acting on includes the truth of our unknown environment of exploration, our onboard observations, and the current awareness and intent of the ground science team members themselves. We're trying to maximize their understanding, and that takes a new approach. So let's start from scratch. What are some of the key drivers that define science autonomy? It's not cost savings, because this is very new research, and that's expensive. It's not reduced mission operations staff, because at first, they'll likely be even more. It's not simpler. Autonomy brings complexity out of our brains and into the spacecraft. And it's definitely not incremental, heritage-based progress. This is a new paradigm. To get something this new on board, we require enablement. We must show that these new capabilities are necessary to achieve new science outcomes. For most autonomy, like landing on Mars, primary drivers are reaction time and communications opportunities. Relativistic delays to distant worlds can be hours, And even near the Earth, long periods of communication blackout limit control opportunities. So if you need to react and adjust to something faster or more frequently than communications permits, you must automate it. But humans are exceptional at intuitive learning using built-in physical models within our brains. If we could, we would joystick our rovers on Mars to this day, and our missions would likely be improved if we did. Keep that point for later. If we didn't have to take humans out of the loop, we wouldn't and probably shouldn't. For science instrument autonomy, limited communication opportunities are only a secondary rather than a primary driver, predominantly for capturing transient science events and efficient use of mission resources when we can't offer guidance. Our primary driver is bandwidth, or the incredible lack thereof at planetary distances. Look at our current communications rate at various planet targets and how swiftly we can take data. Mars enjoys up to 4,000 kilobits per second, while Pluto's drops to a mere 1 kilobit per second. And for the Juno spacecraft at Jupiter, while its instruments are capable of generating 1,000 kilobits per second, they are severely restricted by a mere 20 kilobits per second downlink back to Earth, 50 times less. Now keep in mind, this works. We can and do achieve science progress this way. But what do scientists really want to do? Let's look to low Earth orbit to find out, where bandwidth isn't so limiting. The missions don't just grow in bandwidth, they're larger by 5 to 8 orders of magnitude. NISAR, SWAT, SPG, these are missions that will transform our understanding of the Earth and address burning science questions of the day. Is it that we don't have such questions for the outer planets? Is there less science to do there? No. The science is constrained behind this terrible bandwidth barrier. And in the Owl's case, where we want to send instruments that haven't even been to LEO before, it's not just data velocity. Even a single microscopic movie observation may itself be 40 gigabits, larger than the entire mission downlink allocation for Europa lander. While future DSN upgrades using optical communication may yield 40 times or more increased planetary bandwidth, and we will certainly welcome every bit we can get, we need factors of 10,000 and more. We don't need data compression in any conventional sense like JPEG or MP3. Those work maybe a factor up to 100 and can severely distort scientific conclusions. We need knowledge extraction, and we need to do it using flight computers that make modern laptops look like supercomputers. While we're talking about key drivers, let's talk briefly about how anything gets on a mission at all. These are findings from a recent collaboration between aerospace and JPL, exploring how to better create AI-based autonomy that can be trusted to a mission level. Here are 3 mission stakeholders that any autonomous capability would need to win trust from in order to get a shot at a mission at all. From NASA review panels to the engineers tasked with building the spacecraft, and finally the operators in charge of commanding and safeguarding the hardware, each of these groups has distinct and separate motivations and requirements for winning their trust. But for science autonomy, there are 2 new key stakeholders. As science autonomy sits between mission scientists and their precious raw data, this creates unique tensions and requirements. Rigorous validation and verification just isn't enough. What about biases that the onboard systems will certainly induce during reaction or prioritization? Can I tell why the autonomy did what it did? And can I easily reconfigure it in situ as my evolving science understanding changes? Beyond the mission scientists, the final stakeholder who determines whether a mission has been a success is the worldwide scientific community itself. When mission leaders are standing on the podium announcing that evidence of potential life was returned from Enceladus, we won't be able to just say, the science autonomy is really good, trust us. The community will require multiple overlapping lines of evidence that support skeptical reanalysis and verification on the ground. Earning the trust of these 5 stakeholders defines the guiding principles of impactful onboard science autonomy. So what if we just try to build these onboard science capabilities using standard engineering techniques and approaches that emphasize risk reduction? Well, since physics doesn't allow us to have humans fully in the loop, engineers often want them entirely out of the loop. Write down the fixed performance requirements upfront and exhaustively validate and verify, emphasizing edge cases and known faults. This approach can work, but it results in something like a Roomba in space. It goes through life filtering observations and returning summaries just as it was designed at mission start. And if we know precisely what we want to find, as well as all the things we don't want to find, this can work. Except for one thing. This is extremely challenging for a scientist to trust, especially when the one thing we can be absolutely certain will rapidly evolve once we land on a new planetary surface will be our focus of scientific inquiry. Let's consider a new approach. Focus on maximizing knowledge capture, designed to maximally leverage the rare but invaluable opportunities we do have to communicate with the ground mission scientist. Accept reconfigurability and interpretability as requirements. This recasts the onboard system as a collaborator, not an automator, that's in an interactive partnership with mission ops. Designed hand in hand with scientists, this is an approach that can earn science trust. But of course, all this must be done through the tiny straw of downlink bandwidth constraints. A brief word now on why this moment. Traditionally, instrument autonomy prototypes hitched a ride as small tech demos late in a mission's life just to show what we could do. For this, we had to make do with whatever hardware was already on board. Flight computers like these are already astoundingly slow compared to a modern laptop, due primarily to radiation resistance requirements. But worse, running on the primary bus led to a lot of hand-wringing over the risk posed to all the other processes there. And remember, risk without trust means no-go. But with the recent successes of Mars Helicopter, cell phone processors just became flight heritage. This is a really big deal. For autonomy, this increased processing speeds from a 2004 era cell phone to a 2018 laptop. This is fundamentally enabling for handling large data volumes or velocities on board. Packaging processors like these and a flash drive for data storage into a science instrument's housing modularizes away the shared bus risk and creates a self-contained autonomous instrument that can be generalized and matured agnostic to spacecraft hardware. And now we have the compute we need, and modularity reduces our risk. So what are the new classes of enabled science capture that justify an approach like this? We've already talked about the compelling need for knowledge summarization for any high data volume instrument to unshackle it from the Earth. But transient events like intermittent plumes on icy worlds or roving dust devils on Mars may be over before the first communications opportunity arrives. Other science targets may only be recognizable by the changes they leave on the surface. You just can't downlink huge swaths of the surface twice and difference them just to look for the change between. But that's what we'd need to do without onboard science. Finally, the rare and unexpected. If I sent you to the ultra-dry McMurdo Valleys or Atacama Desert on Earth, and I told you, take a sample, and if it conclusively shows evidence for life, you win $1 million. You would be understandably nervous, for even though Earth is definitely filled with life, these environments are sparse and hostile. But if I said instead, you get to take 50 samples, examine them yourself, and choose the top sample to give me, you'd likely feel much better about winning. That's the idea behind representative sampling and prioritization, to make sure we don't miss great discoveries by simple low-end statistics and bad luck. High data volume instruments, transient events, change detection, and improved sampling and characterization are the primary value propositions of science instrument autonomy. So now we've defined our problem well and the requirements for a trustable solution. Let's show you how we actually can realize this with an actual use case and implementation. The video we just saw introduced the Ocean Worlds Life Surveyor, featuring a comprehensive suite of life evidence gathering instruments that provide overlapping evidence for life, from cellular structures to motion and chemistry. In that suite, 4 of its instruments produce orders of magnitude more data than could be downlinked, and so received onboard autonomy treatment. Today, we'll zoom in on just one of the OWL's instruments, that of a digital holographic microscope and its Autonomous Science Data System, or ASDS. Yes, we do love our acronyms at NASA. The ASDS summarizes observations through the creation of autonomous science data products, or as you guessed it, ASDPs. So what's a data product? Let's take a look. There are three main outputs produced by an autonomous science data system for each science observation. To explore these, let's use a car metaphor. Let's say we made a mission to remotely identify and study cars on Earth, and specifically, we wanted to capture evidence for the rare and elusive SUV. The first batch of outputs are the data products themselves. These are highly bandwidth efficient representations of an observation's content. In this case, a quick summary of the appearance of the car. The second output is the diversity descriptor. This is a short list of relevant facts extracted from each observation. Its purpose is to allow us to ask how different or similar is one observation from another. Even if we're primarily after SUVs, wouldn't it be nice to know that we observe 47 different kinds of cars other than the SUV, and to have at the ready representative examples of each kind ready for downlink? That's what the diversity descriptor enables. Finally, we have the science utility estimate, or SUE. This is a single number that simply answers how scientifically interesting is this observation based on my current targets of interest. In our example, this would be how closely the car matches an SUV from 0 to 1. The SUE allows prioritization of observations so that the most likely informative findings get queued first. Together, these efficient data products, diversity descriptors, and utility estimates enable the full range of onboard science mission capabilities. Each are designed hand in hand with mission and instrument scientists to ensure they support downstream reanalysis, interpretability, and enable reconfiguration of the onboard system as needed. So now let's leave the SUV behind and examine our holographic microscope data from OWLS. Here you can see a movie of the actual 2D images captured by the digital holographic microscope, naturally compressed as a hologram. These represent a full 3D volume movie of liquid streaming past the microscope's field of view. Normally on the ground or in the lab, we'd reconstruct the full 3D movie for a much cleaner view. But remember, we're on board, and even a powerful laptop can take all night to reconstruct a single observation's 5 gigabytes of science data. So for the space case, our onboard system just has to work on the messy, out-of-focus 2D raw data directly. Those bullseye patterns that I've frozen for you in the field of view are objects. Note that most are drifting by passively. Classic Navier-Stokes plus some Brownian motion. They are not evidence for life. But some of those particles are moving under their own power. Your eye is really good at spotting them because your brain has a few 100 million years of evolved hardwired routines to recognize lifelike motion at all times. Picking out these motions, or motility, that substantiate evidence for life is the goal of the system. Doing so in a trustable manner using minimal downlink is the requirement of the mission. And here's how we did it. First, produce a wealth of health and validation products, such as signal to noise, estimates of the background flow rate, and the observation's intensity and stability characteristics. This isn't science, but we need these because if they don't check out, no one's going to believe our claims. Poor quality data doesn't support trust, and we need to support ground ops instrument health monitoring anyway. Next, we summarize the observations with respect to the science goal. We use tracking algorithms to produce coherent tracks for all objects in the view, and a machine learning classifier identifies which tracks resemble lifelike motility. This list of tracks is just a text file, an incredible compression and summary of what matters in this enormous observation. In principle, the text list is the observation, if you trust the tracking algorithm and the machine learning classifier to recognize lifelike motion just like you want. To reduce this burden of trust, a second analysis is performed as shown on the right. This is called a motion history image. It's a single 2D image that summarizes all the motion in the entire movie. No tracker is required, no machine learning classifier. It's simple math. And that makes it an independent line of evidence. Even if a large fish swam through the field of view, which I guarantee you the trackers and classifiers would definitely not handle, there would be plentiful evidence of the event in the history image. To further reduce the burden of trust, we capture regions of raw data surrounding every lifelike motion source as well, so that ground teams can drill into the details and reconstruct them in 3D on the ground. Finally, we produce an overall scientific utility score for how lifelike was the most lifelike motion in this movie, as well as distill key motion characteristics for the diversity descriptor. Here's a workflow view of what we've just said, from raw data to efficient science data products. What's added here is how later onboard systems select among the observations trapped on board to decide what gets sent back to Earth and in what order. This ordering could rely entirely on the utility estimate, returning precisely what we asked to find, or it could rely entirely on the diversity descriptor, returning a representative sampling that spans the differences of motility within the whole set of observations. Using this approach, science planners get to specify the blending between known targets and diversity sampling dynamically throughout the mission. But more on that later. We'll also see here that on the ground, we do not get the full raw data that was trapped on board. We can't. Rather, we have a summarized understanding produced by the intersection of multiple overlapping data products, raw data cutouts, and key background context. Now, this has been just one example of science autonomy built for a holographic microscope, but the principles we've exposed apply to any onboard science instrument. Autonomous data systems, utility estimation, and diversity description can be defined that address any mission science goal, as well as capture the potential for serendipitous discovery and inform instrument health monitoring. But to get on a mission, we need not only have a strong technological approach, but a skilled community that can evaluate and review such a proposal, as well as the trust of our agency sponsors. We don't have those yet today. We need to build it. To scale up these lessons and tackle the larger mission context, we need something bigger. That's why we started Synopsis, the science yield improvement via onboard prioritization and summarization information system, a reusable community framework funded via the Advanced Multi-Mission Operations System in order to accelerate the development, raise the quality, and encourage the infusion of onboard science instrument autonomy. I warned you, we're NASA and we love the acronyms. Synopsis is embodied in three ways. First, as a conceptual framework that provides the workflows, language, and guiding principles that you've been hearing about so far today. Second, as an implemented framework integrated with F Prime, a popular flight software framework for spacecraft. The Synopsis software framework not only provides an interface for existing and future science autonomy, but it also contains a common observation prioritization set of service. So long as instrument autonomy systems comply with the Synopsis definitions for products, utility, and diversity, they can rely on Synopsis to provide robust cross-instrument prioritization. Third, Synopsis offers an open community corral or a common repository for actual implemented instrument autonomy. This will allow researchers to more easily leverage and find past onboard science capabilities to avoid starting each new project from scratch. We are seeding the corral now with some existing JPL examples, and then we'll solicit participation across NASA. The conceptual framework is what you've been hearing about so far, with its data products, utility estimates, and diversity descriptors, but Synopsis extends this into the operations context in some key ways. For example, what happens to all the onboard data that isn't prioritized for downlink? It stays on board, of course, up to the limit of storage. Each time prioritized observations are sent back to Earth, ground operators also receive something totally new, a manifest of all the observations that are on board still. We can't send back the raw observations, of course, but we can describe them simply, everything we have. What's more, using the diversity descriptors, we can compare what's still on board to the observations that were sent down directly. This is a major change from operations today, where you don't get to know anything about what's inside a data product until it's downlinked. In our holographic microscope example, we only considered estimating scientific importance for a single instrument at a time. Synopsis extends this approach to include the possibility that co-observations from two or more instruments might positively or negatively inform each other's importance. For example, on owls, if lifelike chemistry and lifelike motion were observed from the same sampling region using different instruments, you better believe that both observations should have their overall utility increased. There are many such positive and negative cross-instrument, cross-observation relationships that a science mission might wish to encode. Rather than be prescriptive, Synopsis provides a flexible language to encode these cross-dependencies in a general manner. It then provides guidance by thoroughly exploring many realistic mission dependencies and how they may be captured using the synopsis approach. As always, science mission planners are in full control, and these dependencies may be updated mid-mission should an evolving science intent require it. What you see on this graph is a simulated result of how much more swiftly science understanding can increase on the ground with observation prioritization versus uninformed downlink. Even for missions where most observations will be returned, onboard prioritization provides a rapid focus of attention for interesting or important observations that can speed human review of key findings in the operations context. I hope to have convinced you that by now, onboard science capabilities are feasible and mature, important and relevant for upcoming mission opportunities, and that we have defined sound approaches and guiding principles to render them trustworthy, even to the standards of science advancement. But to really secure a place on board, I need to tell you one more piece. How are we going to operate these sophisticated onboard systems? How will science planning evolve in the presence of skilled onboard science autonomy? And that's what we'll talk about next. How do we plan science mission instruments now, and how will that evolve? Let's start with today. It all starts with science intent. Scientists work with mission planners and instrument operators to translate current questions of interest into specific spacecraft commands to acquire observations. Look here, take this observation at this exposure. Planners negotiate the needs across all instrument systems and the spacecraft itself to generate whole sequences of commands that define precisely what we want the spacecraft to do. These sequences of commands are tested and validated in simulators and testbeds to ensure they're safe to the best of our understanding. If they pass, they're uplinked to the spacecraft and followed to the letter. If anything goes wrong or is substantially out of nominal expectations, the spacecraft halts operation and awaits further instructions, resulting in lost precious observation time. If nothing failed, the spacecraft then downlinks the requested observations, which are received and cataloged by mission operations. The science data is passed to ground processing pipelines. Mission scientists wish to pore over the new observations, but they must often wait for ground processing to complete, and the amount of return data will often preclude examining all of it before the next planning cycle. So a lot of information that was returned may not be fully ingested for quite some time. That is what we do today. So how will this change in the presence of skilled onboard science autonomy? The first major change is that some of the raw commands we send today will instead become behavioral configuration files tomorrow. Here's what I mean. Rather than trying to capture the science team's intent in a series of specific observations, we must translate that intent into the behavior for the onboard autonomy to pursue. This is done through configuration, literally a small file of parameters that control the autonomy's behavior, just like any other program on your computer today. By changing these parameters, we communicate to the autonomy what it should attempt to capture, how to process the data, what to prioritize, and how to balance between known targets of interest and characterization of diversity and unexpected discoveries. Creating the right configuration to achieve this requires a new science operations capability. This new planning capability at its core is simply a software simulator, like a testbed, that we can interrogate to find the right configuration for our desired science outcome. To use it, science operators first specify the outcomes they want, outcomes to avoid, and select a distribution of likely raw instrument observations based on the current mission context. For example, if your rover is exploring sandy dunes, you'd only want to optimize the autonomy's reactions over images of sandy dunes. The planning system then launches into action, exhaustively exploring different autonomy configurations and simulating their outcomes on all the likely instrument data you selected as relevant. All these different outcomes and configurations are then brought together in an interactive report. The science planning team may then explore the different families of optimal configurations and their relative trade-offs, because there's never one best answer, just many pretty good ones to decide between. Not only does this system enable dynamic reconfiguration of onboard autonomy, but it supports traceable mission planning decision-making in a statistically defensible manner. We have just begun building these tools today. After planning, the configuration is uplinked to the spacecraft like the commands today. But where before the spacecraft held only buffered data for downlink, we now have a whole new world. A rich, complex, curated onboard data product archive, raw data, summarized products, and a manifest describing their interrelationships and similarities compared to those already downlinked. Scientists may manually request the downlink of any product at any time, along with uplinking new definitions of known targets or priorities. Each interaction with the system increases the insight and awareness of the ground team and refines the mission's current scope and focus. Science planning is no longer just about observation acquisition. It's also about exploring what's already been captured on board, a mission into the data. We've almost come to a close, and I hope you can feel some of my passion about the promise of these approaches and possibilities. I said at the beginning that none of this is going to get on board with anything short of enablement as a primary driver for mission inclusion. Let's take a moment now to see just one example of such a mission that simply could never be without onboard science support. Because you see, Mars is a dynamic place. Dust devils race, rocks fall, and something keeps oozing down steep slopes, leaving dark tracks. Enigmatic small dust uplift events sometimes just peter out, while in other cases they grow into global storms. Meteors smash into the surface, ice sublimates and reforms, and volatiles explosively outgas in great dark plumes. The Mars Reconnaissance Orbiter, or MRO, has seen it all. But most of these dramatic, dynamic, changing processes have been captured by accident, because knowing what changed on Mars requires differencing an old and a new image, and we simply can't downlink enough data to do much differencing back on the ground. So, no joke at all, much of this changing science has been discovered by graduate students pouring through data archives while looking for something else. We know it's happening, but we don't well know how much, where, and when. And using today's mission concepts, we never really will. For example, MRO's high-resolution camera was designed to only return a single image a day, because why bother to take more? We can't afford the bandwidth. So instead, imagine MRO's beautiful cameras as they are now, but equipped with computers and autonomy. They are always on, processing every photon that comes in. They are reducing those complex images to summaries of known surface features and very efficient descriptions of general morphology that can be stored on board in a global archive. In only about 2 terabytes or so, such a mission could actually monitor the entire planetary surface for change without using any downlink at all. Slowly building up a report. What's changing on Mars today? Where change is occurring? And what known processes does it look like? When the time for communication finally comes, rather than raw imagery, a comprehensive global report is sent. Small cutouts of raw data surrounding regions of change support later inquiry. Heat maps of known targets of interest are returned across the whole surface, and ground-specified regions of high interest are monitored to the pixel level for the onset of anticipated seasonal activity. Best of all, the massive onboard database of scientific observations, impossible to ever downlink due to volume, may still be explored and published on as scientists uplink efficient queries or even analyses for the onboard system to consider. This is the ultimate in edge computing, a true orbital science station, collaborating with Earth to produce an ever-improved understanding of the Martian surface. And all that's needed are some onboard smarts, a flight computer that's now heritage, and some flight-hardened flash drives. Wow, right? Well, after that vision, where are we? Will this stuff ever get into space? How real is all of this? The road to the first mission truly enabled by science instrument autonomy is long. It began with early prototypes and opportunistically sneaking in on missions after their primary level 1 requirements were met, just to show feasibility and potential. That part's done. Then we moved on to actual deployed systems demonstrated improved mission science yield and acceptance by planners and operators. That's done too. The Mars helicopter brought flight computing into the modern era. Done last year. Building science autonomy for an entire suite of interacting instruments with overlapping evidence. Last year also. Building ops tools capable of controlling these advanced capabilities. That's about to get underway. Intersecting these capabilities with the recent planetary decadal survey and socializing these achievements to earn a place among the broader NASA autonomy community? Well, you're helping me do that right now. This talk is part of that education, outreach, and infusion effort to win visibility and acceptance. And hopefully among this audience, there are planetary scientists who are already starting to dream bigger, pose bolder questions, and realize the shackles of bandwidth are beginning to slip off their wrists. Sure, we need to settle a few more onboard resources, like massive data storage. And as of this moment, there aren't any NASA Rose's proposal calls that directly address or mature this new kind of autonomy. But there will be. And those will result in a handful of reusable, trustable, killer apps for onboard science that will grow, mature, and finally earn their place among the stars. But most importantly, they'll bring the stars back down to us, bandwidth barrier or no. I hope I've inspired you today to consider that a future with skilled onboard science autonomy is already in the making, ready to unshackle yet more earthbound instruments and break that bandwidth barrier. I call on everyone to help us on this next leg of the journey as we build a community of science autonomy developers and win the trust of scientists and mission managers alike. Thank you for coming on this journey with me today. If you have a question, go ahead and type the word question along with your inquiry into the Q&A box now. And thank you.
Our first question is from Mark Raymond. Go ahead.
Hi, Lucas. I thought that was fascinating. Thank you. Can you say anything about how JPL's work on, excuse me, on science instrument autonomy compares with what other organizations in the US or elsewhere are doing, whether for space exploration or for terrestrial applications?
Absolutely, I would love to. So in the industry, there's an enormous amount of work, as you well know, and has been in autonomy for some time. Self-driving cars are one of the common ways that we see it as civilians, but there have been autonomous missiles and military hardware for quite some time. Those are very different than science autonomy, however, because there you do not want the human to decide they don't quite like how their car is handling when it drives over grass versus asphalt, so they get to tweak the parameters of the autonomy. We want to lock those down and make them like the Roomba example. So the ability to reconfigure and learn from the autonomy is dramatically different than what the industry is focusing on. Other centers like Goddard Space Flight Center are acknowledging that this is an important future capability and have started to recently publish papers in the field, but currently JPL enjoys a lead in the area.
Our next question is from Bruce Wagner. I'm going to go ahead and unmute you. Okay, Bruce.
I had a question about uplink. Has your group thought about how much uplink volume is required to potentially adjust an autonomous instrument and whether that would swamp the current uplink capabilities of our spacecraft?
Absolutely. So the uplink is kept to an absolute minimum. We're talking about literal configuration files. We're not uploading any significant data of any kind, so it should be well in bounds of the current uplink behaviors.
Our next question is from Jonathan Sauter. You have been unmuted. Go ahead and ask your question.
Thanks. Yes, I was wondering if, optical communication becomes something that in, 10, 15 years becomes the basis for future missions, how does that influence the bandwidth challenge? And would this reduce the demand for level of autonomy required?
So in principle, it reduces some of it, but as some of the previous slides showed, optical comm is probably going to be aspiring up to maybe 40 times our current bandwidth, but to do what we need to do out there is requiring factors of 10,000. So no matter what, we're going to need this stuff when we go to the outer planets, even if optical comm becomes a full reality. And even if we had 10 times the current number of satellite dishes in the world, we still haven't got to the orders of magnitude that we need.
Our next question is from Brian Sutton. Hold on a second, let me unmute you. Okay, Brian.
What about uploading Python source directly? What are your thoughts on allowing scientists to really go to town?
Well, as I said, it's all about risk and trust. And it would be a very interesting color that I think the engineers would turn if we suggested the ability to upload any kind of dynamic interpretable language in that way. However, the ability to uplink analysis requests, most likely in a precisely coded language that was provably safe, is entirely possible. So imagine a highly restricted MATLAB where you still get to request mathematical operations. But being able to actually just put Python on orbit on a mission that costs $1 billion, I think it would be very difficult to close that trust proposition.
Excellent. I suspect that, you know, a limited MATLAB would probably be perfectly adequate.
It would be an enormous advancement from where we are now, and maybe a future me that enjoys that ability will see the next step that we can aspire to then.
That concludes our Mission Chronicles talk for June. Thank you, Lukas, for that fascinating talk. And thank you to all those who have attended. Thank you.